NENOMATICA, where mathematics meets YouTube excellence. Welcome to this math tutorial. Today, we're going to learn how to factor expressions using the cube of a sum identity. Let's start by understanding the cube of a sum identity. This identity states that a plus b cubed equals a cubed plus 3, a squared b plus 3, a b squared plus b cubed. Now, let's look at an example where we can apply this identity to factor an expression. In our first factoring problem, we'll work with x cubed plus 3x squared plus 3x plus 1. To factor this, we'll first try to recognize the pattern. Let's rewrite this expression to match the pattern of the cube of a sum identity. We can rewrite this as x cubed plus 3 times x squared times 1 plus 3 times x times 1 squared plus 1 cubed. This matches our identity formula, where it is x and b is 1. Now, we can see that this matches our cube of a sum identity where a equals x and b equals 1. Therefore, the factored form is x plus 1 cubed, or x plus 1 times x plus 1 times x plus 1. Let's move on to our second example. We have 8x cubed plus 12x squared plus 6x plus 1. Let's try to match this with our cube of a sum identity. We can rewrite this as 2x cubed plus 3 times 2x squared times 1 plus 3 times 2x times 1 squared plus 1 cubed. Now, let's check if our rewritten expression matches the cube of a sum identity. Looking at the coefficients, 2x cubed means 8x cubed. 3 times 2x squared means 12x squared. 3 times 2x means 6x. And 1 cubed is just 1. These match our original expression perfectly. Now that we've identified the pattern, we can see that this matches our cube of a sum identity where it equals 2x and b equals 1. Therefore, the factored form is 2x plus 1 cubed, or 2x plus 1 times 2x plus 1 times 2x plus 1. Our first example is the expression x cubed plus 15x squared plus 75x plus 125. We need to factor this expression completely. We need to recognize what kind of pattern we have here. This looks like a cubic expression that might be a perfect cube. Let's see if we can express it using the cube of a binomial pattern. Looking at our expression, let's try to match it with the cube of a binomial pattern. If we compare our expression with the formula a cubed plus 3, a squared b plus 3, a b squared plus b cubed, we can identify the terms. Now that we've matched our expression to the cube of a binomial pattern, we can write our expression as x plus 5, all cubed. Let's try another example. This time, we have 27a to the 6th power plus 54a to the 4th power bc plus 36, a squared b squared c squared plus 8b cubed c cubed. Just like before, we need to recognize the pattern. This also looks like a perfect cube expression. Let's try to identify what terms would be a and b in our cube formula. Looking at our expression, we need to identify what our a and b terms would be. The first term is 27a to the 6th, which must be a cubed. So a must be 3 a squared. The last term is 8b cubed c cubed, which must be b cubed. So b must be 2bc. Now let's verify if the middle terms match with our identified a and b values. Using a equals 3 a squared and b equals 2bc, let's check if the middle terms match the expected values from our formula. The middle terms match perfectly, so our expression can be factored as 3 a squared plus 2bc, all cubed. In summary, we've learned how to factor cubic expressions using the cube of a binomial pattern. Let's look at our example. We need to factor the following expression x cubed plus 3x plus 3 over x plus 1 over x cubed. The first step is to rewrite this expression in a way that reveals a pattern. We can rewrite this as x cubed plus 3x squared times 1 over x plus 3x times 1 over x squared plus 1 over x cubed. Let's look at this expression more carefully. We can see that it follows the pattern of a cubed binomial. A cubed plus 3, a squared b plus 3, a b squared plus b cubed, which equals a plus b cubed. Therefore, our expression can be factored as x plus 1 over x cubed. This is our final answer. Let's verify our answer by expanding x plus 1 over x cubed to see if we get back our original expression. Using the binomial cube formula, we get x cubed plus 3x squared times 1 over x plus 3x times 1 over x squared plus 1 over x cubed. Simplifying the middle terms, we get x cubed plus 3x plus 3 over x plus 1 over x cubed, which matches our original expression. Let's summarize what we learned. We identified that our expression follows the binomial cube pattern. By recognizing that it equals x and b equals 1 over x, we were able to factor the expression as x plus 1 over x cubed. This problem demonstrates the importance of recognizing algebraic patterns when factoring complex expressions. Thank you for watching this tutorial on factoring polynomial expressions. Practice identifying these patterns in other problems to strengthen your algebraic factoring skills. The expression we'll be looking at involves cube roots and nested square roots. Let's start with our problem. We need to find the value of cube root of square root of 50 plus 7 plus cube root of 7 minus square root of 50. First, let's observe that the square root of 50 can be simplified. Square root of 50 equals 5 times square root of 2. So our expression becomes cube root of 5 square root of 2 plus 7 plus cube root of 7 minus 5 square root of 2. Now, for step 1, we need to recognize that each of our radicands, that is, the expressions inside our cube roots, can be written as perfect cubes. Let's start by computing what 1 plus square root of 2 cubed equals. Using the binomial expansion, we get 1 plus 3 times square root of 2 plus 3 times square root of 2 squared plus square root of 2 cubed. Simplifying, we get 1 plus 3 square root of 2 plus 3 times 2 plus 2 square root of 2. This further simplifies to 7 plus 5 square root of 2. Similarly, for 1 minus square root of 2 cubed, we get 1 minus 3 square root of 2 plus 3 times 2 minus 2 square root of 2. This simplifies to 7 minus 5 square root of 2. Did you notice? The expressions inside our cube roots are exactly these results. This means we can rewrite our original cube roots using these perfect cube patterns. Now for step 2, we can take the cube roots of these expressions. Since 1 plus square root of 2 cubed equals 7 plus 5 square root of 2, the cube root of 7 plus 5 square root of 2 equals 1 plus square root of 2. And similarly, since 1 minus square root of 2 cubed equals 7 minus 5 square root of 2, the cube root of 7 minus 5 square root of 2 equals 1 minus square root of 2. For our final step, we add the results. We have 1 plus square root of 2 plus 1 minus square root of 2. The square root of 2 terms cancel out, leaving us with 1 plus 1, which equals 2. Therefore, our answer is 2. This demonstrates an elegant use of recognizing patterns in radicals to simplify what initially looked like a very complex expression. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.